Now let's do one more example. Suppose you have some AC source. Now this AC source, you can also imagine it as, I don't know, you have your headphones, you connect it to your MP3 player. That MP3 player, you can just treat it as an AC source. So it will be a superposition of many frequencies. And then here, let's assume that you have a resistor. And this resistor can be your earpiece, for example. You're listening at some music from your MP3 source. Your music will basically be it will be an EMF source, but it will be an EMF source which contains many frequencies. This is your music. It will have both low frequencies and high frequencies. Now, what will be the current in the resistor? Well, the current in the resistor will determine what you hear. Let's take a limit, some limiting cases. Let's just consider an oscillation that is when omega is very, very small. So it's almost a DC current, and you are waiting long enough. If omega is very small, then what will happen to the capacitor? Will it be fully charged after some time? It will be fully charged, right? After some time. So if it is fully charged, then there won't be any current going through the capacitor, and all the current will go through the resistor. So on the resistor, small frequencies will arrive at the resistor. Now let's go to the other extreme, when omega is very large. Well, when omega is very large, the current is constantly changing its direction. At one instant it is, let's say, flowing downward across the capacitor. At the next instant it is flowing upward in the capacitor. So will the capacitor be ever charged? It is constantly, at one instant it's getting charged, in the next instant it's getting discharged. There is no charge accumulation on the capacitor. So if there is no charge on the capacitor, it will just behave like a short circuit. If it is a short circuit, all the current will run through the capacitor, and no current will run through the resistor. So it basically means that low frequencies will reach the resistor, but high frequencies will not reach the resistor. Well, if the resistor is your speaker, so what kind of a sound will you hear? The low frequencies? Yeah. Low frequencies, you just hear this thick sound. Well, let's do some alternatives. So this is what's called a low-pass filter. Now this will be even better. You see, okay, the capacitor will not allow high frequencies to go through the resistor, but so will the inductor, because the inductor resists change. So if the frequency is changing very fast, the inductor will not allow the current to build up. So this will be an even better low-pass filter. So both the inductor and the capacitor will prevent high frequencies from reaching the resistor or your loudspeaker. Let's change the positions of the inductor and the capacitor. So suppose you look at a very low frequency. It's almost a DC current. It doesn't change its sign. After you wait for some time, the capacitor will be fully charged. And since there is no oscillation, there is no reaction, the current is practically not changing, the inductor will just behave like a short circuit. So all the current will run through the inductor at low frequencies. So low frequencies will not be able to reach the resistor. Whereas if you have a high frequency, if you have a very high frequency, the inductor will create a large back EMF. It will prevent the current running through it at high frequencies. But the capacitor, on the other hand, since it won't be able to be charged significantly, it will just let all the high frequencies pass through as if the capacitor doesn't exist. So basically, it just allows the high frequencies. This is called a high-pass filter. So how will you hear it? Very? Which sounds like? Can you mimic it? You will hear this very thin sound. So this is basically how you change the sound in your speakers or the hi-fi systems.
If we could detect the vibrations in our throat when we speak, when we speak in a high-pitched voice and a low-pitched voice, can we detect the vibration frequency like matching what we assume?
Sure. Well, basically that's how Stephen Hawking is speaking, by the way, by detecting the vibrations over here.
I think he's speaking like using laser something.
Well, he used to use this one, and now I don't know if he's able to speak or not.
Can you say why it's different, this situation? Yeah.
You see, the behavior of a capacitor and an inductor. If you attach a capacitor to a DC circuit, after some time it gets fully charged, after a very short time if there is not much resistance, and once it is fully charged, it will not let any current pass. So that is the low frequency. Low frequency just means that the current is not changing much in time. It is slowly changing, but if it is slowly changing, all the time the capacitor is fully charged. So if it is fully charged, it will not let the current pass through. In this case, also in the above case, it's basically the same principle. At low frequencies, the capacitor doesn't allow the current to pass. On the other hand, the inductor at very high frequencies, remember, at high frequency current just means that it is changing very fast. But if it is changing very fast, it will be creating a large EMF, a so-called back EMF in the inductor, which will prevent the current to pass through the inductor. So at large frequencies, the inductor just behaves like an open circuit, whereas the capacitor behaves like a short circuit at high frequencies. At low frequencies, the capacitor behaves like a closed circuit, no, open circuit. It doesn't allow the current pass at low frequencies, whereas the inductor behaves like a short circuit. You see, if you also go back to this expression over here, it is also apparent over here. If you are at very low frequencies, when omega is very small, this term prevents any current from flowing. Well, this is due to the capacitor. The capacitor at low frequencies doesn't allow any current. If you are at very high frequencies, then there is no current because of this term over here. So that is the inductor. The inductor doesn't allow any current that has a very high frequency to pass through it. That is why these simple circuits over here they basically filter frequencies. One allowing only the low frequencies to reach the resistor, the other one allowing only the high frequencies to reach the resistor.
This may or may not be related, I'm not sure. That's why I'm asking. I've recently noticed that headphones have magnets in them. Headphones have magnets in them. Why do headphones have magnets in them?
The speakers.
Yeah.
Well, how do you cause the vibrations in the diaphragm? You see, how do you create the sound? Your throat creates sound by vibrating strings. A guitar creates sound by vibrating strings. A loudspeaker also creates sound by vibrating membranes. It has a membrane also. And how does the membrane vibrate? This is your membrane. Well, there are various things you can do. You can attach a magnet to it and then put a coil over here. So if you change the current in this coil, the force between the coil and the magnet will change. So if you change it fast enough, you will be vibrating this membrane over there. So this is a simple loudspeaker. Sorry?
Is the material of the membrane
The material, the size. So if you ever have seen any speaker systems, 5.1 speaker systems, there is a bass there, for example, which is huge. And in these small earphones, you cannot hear the bass. Low frequencies you cannot create in small membranes. You need large membranes to create low frequencies. Other questions?
So we use different kind of types to create other frequencies. Like we use for low frequencies and küçük hoparlörler.
Yeah. So that is because of the size, mainly.
How can a speaker produce multiple frequencies at the same time?
Well, just send an electric signal that contains multiple frequencies.
The superposition of two frequencies?
Yeah.
Is there a limit to the superposition, the number of frequencies that can be
No,
superpositioned?
not really. Well, of course, there are the limits, like if you, a small loudspeaker cannot create very low frequencies. That is the limitation. A very large speaker, it will be very hard to create low frequencies. There are practical limitations. Other questions? Yes. Well, that will be a nice homework question, for example. For a given omega, how does the maximum current running through the resistor change as a function of omega? Good. You already know everything to solve that problem. You know the Kirchhoff's rules. Just write them and you need to solve them. Other questions? Other homework questions? I still need to prepare your homework. Okay, let's look at the power. Okay, what is the power of an inductor? Nothing really. The inductor doesn't dissipate power. Neither does the capacitor. None of them dissipate power. The only thing that dissipates power are the resistors. So let's look at the power dissipated by the resistor. We already said that the power of a resistor is given by I squared R. And now we are also saying that I is basically, in these AC circuits, is I0 cosine omega t plus delta. So the power dissipated by the resistor will be I0 squared R times cosine squared omega t plus delta. So this power will just change from, will just behave like this. It will be go to some maximum value 0, maximum value 0, maximum value 0, etc. Now, of course, for example, in city electricity, this oscillation is like 50 times a second. And our devices usually do not measure this instantaneous power. So what they would actually measure is what's called the average power, so the power at the time t. The average power is mainly defined as, you just integrate the power over one full period of oscillation. And then this is nothing but I0 squared R over 2. This is the average power. Now this quantity I0 squared over 2, it is usually defined as IRMS. Now this IRMS is I0 over square root of 2. That's why the maximum potential difference created by the city electricity is not 220. It is this RMS potential is defined as 220. Now we can define the VRMS similarly by V0 over square root of 2. Now this RMS is called the root mean square. Well, those offs, they are not there. You take the square of a function, and for an arbitrary function, you can define the RMS value. You take the square of that function, you average that value over one period, and then take the square root. That is what we call the root of the mean, the average of the square of the function. Well, this will be what your devices will be able to measure. Well, this is the average power. This is the average power or the average current that runs through the circuit. For example, when you take a voltmeter and connect it to this, well, not over here, but over there, what you will be able to measure is not the instantaneous value of the potential, because your device, your voltmeter, will not be sensitive to that one. But what you will measure is the averages. And that average is given by these RMS values. It's the typical strength, let's say. The maximum is an exceptional case. The minimum is an exceptional case. The typical value will be this RMS value. This one. Oh, sorry. You were here. Okay.
How long those two? Why is it on t?
Now, 1 over t from 0 to t of cosine squared omega t plus delta dt, this is equal to 1 over 2, where t is 2 pi over t, omega. I mean, if you calculate that integral, this is what you will obtain. It's just 1 over 2. Or you can also say this one. This shape over here will exactly fit this empty place over there. So the area below this curve is equal to the area below this dashed curve, dashed line, which is halfway. This is P max. This is P max over 2. Now okay, any questions on this one? This is just a definition of the RMS. Well, of course, you can just say the average power, this is equal to I RMS squared R, which is equal to I RMS times V RMS. No. It goes from 0 to 1, 1 to 0, 0 to 1, and between 0 and 1. The average is just 1/2. Well, you see, the current itself goes from 1 to -1 and back. So the average of the current itself is 0. But the power is proportional to the current squared. The current squared goes from 0 to 1 and back to 0. It never becomes negative. So the average can never be 0. Any questions? Now let's look at there will be one more interesting thing, the power delivered by the EMS source. Now we had defined the power delivered by the EMF source to be I times epsilon. Well, that was the definition of the EMF. So the EMF is the energy given per unit charge. So if you have lots of charges passing through your EMF source, you just multiply the EMF by the charge. That gives you the total power, total work done by the EMF source. The power is the work done per unit time, so it will be the EMF source multiplied by the charge per unit time, but that charge per unit time is nothing but the current running through your EMF source. We can just say, let's say, cosine omega t plus delta. EMF source, let's say I0. EMF source will be epsilon 0 times cosine omega t. So this is the instantaneous power. Or this will be I0 times cosine squared omega t times cosine delta minus I0 epsilon 0 cosine omega t sine omega t sine delta. Now again we can define the average power. The average power will be I0 epsilon 0 over 2 times cosine delta. Now if you just take the average, do the averaging over one period of this function, it just gives you 0. This we can also write as I RMS, epsilon RMS times cosine delta. You see that it depends on delta, the phase difference. Now if you, let's go back. Now this delta, if R is equal to 0, then this delta over here is actually 0. So that's basically what we had already knew. No, the inductor and the capacitor, they don't use energy. They don't use power. They store it and then give it back. There is no dissipation. It is the resistance that causes the dissipation. So that is why if the resistance goes to 0, there is no power. So for example, if you just take a charger, put it in a circuit, In an ideal charger, unless you connect it to your device, it will not use any power. Although there is some current running through it, it will be constantly changing, but no power will be used. It's only when you connect it to your device that you want to charge, it's only then you start using the power. Of course, this is the ideal case. In a realistic case, the charger itself has its resistance, and since it has its own resistance, it will be consuming power, but it will be very small. It will not be transmitted anywhere. Any questions on this one? Well, there's basically one more thing I would like to discuss today before you go. Let's look at this one. The power dissipated by the resistor is I squared R, and we said that, okay, we could write it in terms of the RMS current, RMS current squared times the resistance. So if the RMS current is very small, then basically there won't be any power dissipated. So what we want? Okay. If the RMS current if the current is small, there won't be any power dissipated. Do you agree? So we somehow want to modify the currents or the potential. If you change the current, you are basically changing the EMFs. So that is what we would like to do. And the device that allows us to do it is the transformers.
About the powers by the epsilon. Okay. The last one was IRMS times epsilon RMS equals cosine delta. And the last one you said R is equal to 0, delta is equal to 0. Why not cosine delta, cosine 0? That means it's 1.
Sorry. Okay, there is one more thing I'm cheating on, by the way. The conventions. And you have to be careful about how you define this delta. Now, this delta over here, tangent delta, is equal to XL minus XC over R. It's wrong, right? No. When R goes to 0, tangent goes to infinity, that means cosine delta is 0. Well, you see, what we had done is, before this was sine, right? In that derivation. I just switched some conventions. If you don't want to switch conventions, this will be sine, and eventually this will be sine. And then sine delta will be 0. R over XL minus XC. How do? Which one? This one. This is our previous definition. If you have a series circuit with RLC, this is how you define the phase difference.
So this concept of delta, we define some things, mostly EMF sources. Without delta, we define the currents and but with the delta. And you say it's the phase difference. It doesn't make intuitive sense. I can't just grasp it.
Well, okay, this is some terminology that you will be hearing a lot next semester. when you are taking circuits, electronic circuits, 2 or 3. So this is kind of getting you preparing for that course. Now, what this delta is, now thinking in terms of the power dissipated, the power can only be dissipated through a resistor, right? So if in your circuit there is no resistor, then there is no dissipation of power, so your EMF source basically cannot deliver any power to your circuit if there is no resistance. So this sine delta is equal to 0 is basically that statement, that there is no resistance in your circuit. Now, if you put some resistance, then your EMF source will deliver some power. And that power will depend on how your resistance compares to the inductive and the capacitive reactances. And in fact, the maximum power you can deliver if XL is equal to XC, when you have a resonance. Now, that is also what we expect. That is the basic idea of the resonance. When you have a resistance, the current is a maximum. Since the current is at a maximum, the resistance just dissipates the maximum power. So that's another way of looking at the resistance. So this statement is also just a mathematical expression of that fact. In resonance, you deliver the maximum power. So if you want to deliver the maximum power, then you need to create your system in resonance.
But visually speaking, can you visually demonstrate the difference between omega t and omega delta in writing the
Beyond this one,
like this? Is that what we demonstrate?
yeah, this is how we define the delta. Now, I wouldn't really know how to give what other visual explanation of that.
Because as I said, these are very counterintuitive things. We can't see them.
Well, basically the delta is, you see, there is an EMF source. It is driving the current. But for some reason, and this reason is due to the capacitance, inductances, and the resistances in your circuit, when the EMF is at a maximum, your current is not at a maximum. The current is kind of approaching the maximum at a later time.
So that's why we have the delta.
That is why we have the delta. So they are out of so-called they are out of phase unless you are at a resonance point. In a resonance point, both of them will be in phase, and since both of them are in phase, the power delivered will be a maximum. Now, when they are out of phase, you see, this is always true for the power delivered by an epsilon, by an EMF source. This is always true. Now, if they are not in phase, that basically means that the current will not be at the maximum when the EMF source is at the maximum. They will not be at the maximum at the same time if they are not in phase. But that basically means that the power will not be the maximum possible that you can deliver. Only if both of them become maximum at the same time, the power delivered by the EMF source will be at the maximum. Only if both of these quantities become maximum at the same time. Now let's look at the transformers. Okay, so the basic idea is this one. You get a ferromagnet. Okay, so a ferromagnet is a material that enhances the magnetic field strongly. And you get two solenoids. This is one of them. This is the other one. and you attach an EMF source to that one. So there is, let's say, N1 turns over here, there will be N2 turns on that one. Now the ferromagnet is something nice in the sense that it kind of traps the magnetic field lines. The magnetic field, I mean, if you have such a loop, if it forms such a loop, all the magnetic field lines will prefer to go along the ferromagnet. So if you just send some current in the primary coil, this is called the primary coil. This is called the secondary coil. If you send some current through the primary coil, it will create some flux in the first coil. Now let phi 0 be the flux created per ring. For each ring, there will be a corresponding flux. Now, the magnetic field lines will be trapped in the ferromagnet. So whatever flux you create over here, it will also be going over the secondary coil. So the phi 1 over N1 will be equal to phi 2 over N2, since both of them are equal to phi 0. Phi 1 flux through the primary coil. And phi 2 is the flux through the secondary coil. Now, if these two are equal, if we just calculate d phi 1 by dt, 1 over n1 will be equal to 1 over n2 d phi 2 by dt. Their time derivatives will also be equal because the fluxes are equal. But the time derivatives are nothing but epsilon 1 and epsilon 2. Do you agree? So basically, by applying a current through the first one, and by applying an EMF to the first one, you are creating a potential difference, let's say, between the two terminals over here, and that will be creating a potential difference. That will be creating a current running in the secondary circuit, and by basically creating an EMF between these 2 points. And the ratio of the EMFs are given by the ratio of the coils.
Potential depends at the same root of coil. Potential depends at the same.
Well, you see, the EMFs are not the same. Epsilon 2, this is the EMF created in the secondary coil, is just N2 over N1, epsilon 1. So they are different. If the number of coils are different, they will be different.
I have a notation. Can you show us this EMF producer? Does that always be an alternating EMF producer or just any?
Now, it cannot be any EMF source. The reason is this one. If you want to write this equality, d phi 1 over dt. Well, if you, for example, put an AC source, a single AC source, a DC source, that's an EMF source, then it doesn't create any flux. So this is 0 equal to 0.
So now, I understand that for both conventions, that symbol always means an alternate.
Now this will be, the symbol you mean, this one. It will mean an AC source all the time. And well, it doesn't specify the frequency. The frequency can be very close to 0, but it will always imply an AC source. So your charges for your devices, they are basically using this principle. So you connect it to 220 volts, but your device needs, let's say, depending on your device, it needs 12 volts, not more than that. So what you do is, epsilon 1 is 220, and epsilon 2 is equal to, let's say, 12 volts, and then you can determine what the ratio of the turns should be. 12 over 220. So if you make a transformer, those charges contain a transformer, can contain a transformer with this ratio of the turns. If you open them up, well, probably this one also has one in it. Did you open up a transformer or a charger? How many of you did it? Okay, so when you find a broken one, open it up. You will see that they are not, this ferromagnet over here, they are usually using iron. They are not just one block of iron. Yeah, you can have various shapes. Most of them will have such a shape with a hole inside. And you just wrap your wire around here. But most of the time, they will not be block of iron, but you will see that they are layers. They are so-called laminated. What's the point? There is no current. They have to be insulated. The wires do not touch the iron. They are insulated from each other. So which current? The eddy currents. You see, we had seen that if you have such a solenoid, there will be electric fields induced inside, circular electric fields. So this is I. But those circular electric fields, if you have a conductor like iron, so you will be creating currents. But those currents, iron has not such a small resistivity, so iron will resist the current, so it will dissipate the power, and it will become hot. So that is not what you want. So what you do to prevent these, the currents will be basically just going in circles, the eddy currents. To prevent them, what they do is they just break this iron into layers of iron, and each layer they are insulated from each other, so that the eddy currents will not be able to go around, but they are confined to very thin layers, and you will not be getting any currents in that one, or very small currents. So that the transformers are made in this laminated fashion to prevent losses due to the resistivity of the iron. Now let's look at, Now we will discuss it a bit more on next week. Just a point, you see, if there is I1 running over here, there is I2 over here, you cannot create energy. So the power delivered by the primary EMF source by the primary coil, let's say epsilon 1 I1, this should be equal to epsilon 2 I2 to conserve energy. So if you are increasing the potential, you are lowering the current. And the power of a resistor is, remember, I squared times R. So using a transformer, you can lower the current, increasing its EMF, the corresponding EMF. So if you lower the current, there won't be any dissipation losses. And basically that is why in the transmission lines between cities, you have the high voltage transmission lines. Because those high voltage transmission lines, they carry very small current. And since they carry a very small amount of current, they will not dissipate energy. And then when it reaches our homes, it is stepped down from 10,000 volts to 220 volts close to the houses. And then we can just use it safely at home. Okay, any last minute questions?
I have actually Googled the transformer and seen that it is not, it's not looking like this. It's an iron block.
It is?
It's an iron block, but it has something inside about the ground. It has two coil lines inside the block of iron.
2 coils inside 1 block.
Yeah. I'm going to show you a picture.
Okay. Okay, so have a nice weekend and see you next Wednesday.